This video will work through the 2015 question on satellites from the NCEA paper. So we're given the mass of the Earth and the universal gravitational constant, and we're told that digital television in New Zealand can be accessed by using a satellite dish pointed at a satellite in space. The satellite used to transmit the signals appears to stay still above the equator. The satellite, with a mass of 300 kilograms, is actually traveling around the Earth in a geostationary orbit at a radius of 4.22 times 10 to the 7 meters from the center of the Earth. So this is R. We're given M, and we're given big M here, the mass of the planet. And we also know the time period because it's geostationary. So we know that T equals 1 day. Okay, question A says, name the force that is keeping the satellite in the circular orbit. That's the force due to gravity. And state the direction in which this force is acting. So it's acting towards the center of the Earth, or the orbit. Calculate the force acting on the satellite. Well, the force is the gravitational force, and we know that F is equal to G M over R squared, which is equal to 6.67 times 10 to the negative 11 times the big M was 5.97 times 10 to the 24 times the little m, which was 300, and that's all divided by R squared, which is 4.22 times 10 to the 7 squared. So it's 6.67 times 10 to the 11 negative times 5.97 times 10 to the 24 times 300 divided by, and the radius was 4.22 times 10 to the 7. Was that meters or kilometers? Let's have a look. Meters. And then we want to square that. And that is equal to 67 newtons. Okay. It said the force, it didn't say the size of the force, so we should really say downwards towards Earth's center. C says, show that the speed of the satellite is 3.07 times 10 to the 3 meters per second. Okay, and we have two options here. The easiest one is to do this, is to say Fc is equal to Fg, and so mv squared over r is equal to gmm over r squared, and then we can cancel one of the r's, cancel the m, and we get v is equal to the square root of gm over r, which is the square root of 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24 divided by the radius, which was 4.22 times 10 to the 7, all square root. So 6.67 times 10 to the 11 negative times 5.97 times 10 to the 24 divided by 4.22. It was 22, right? Yes. Times 10 to the 7 gives us, and then we want to square root that, and that gives us 3072 meters per second, or 3.07 times 10 to the 3 meters per second, which is what we were looking for. Alright, then we have Kepler's law states that for an orbiting object, t squared is proportional to r cubed, where r is the radius of the orbit and t is the time period for the orbit. NASA uses a robotic spacecraft to map the moon. The Lunar Reconnaissance Orbiter orbits the moon at an average height of 50 times 10 to the 3 meters with that period, and the moon has a radius of this. Use Kepler's law to estimate the mass of the moon. In your answer, you should use the relevant formulae to derive Kepler's law and use Kepler's law to determine the mass of the moon. Okay, so with this question, we don't need to worry about the fact that we don't know Kepler's law, because we're told what Kepler's law is. It's the relationship between the time period and the radius. Okay, so to derive it, what we'll do is we'll use the derivation we've already done, which was that V is equal to the square root of gm over r, and that's from question C. And the fact that for anything moving in a circle, V is 2 pi r over t. So if we make these two things equal, we get the square root of gm over r is equal to 2 pi r over t. If we then square both sides, we get gm over r is equal to 4 pi squared r squared over t squared. And we wanted to show that what t squared is proportional to r cubed. So we'll just rearrange to put t squared on one side, r cubed on the other, and the constant we'll put with the r cubed. So therefore we get t squared. So we multiply both sides by t squared, and we'll multiply both sides by r. T squared gm is equal to 4 pi, t squared times gm, 4 pi squared r cubed. So t squared is equal to 4 pi squared over gm times r cubed. So that is Kepler's law, because this is all a constant. We can say that as 4 pi squared over gm is constant, this shows t squared is proportional to r cubed. And then we want to use it to find the mass of the moon. So we're given the period and we're given the height and the radius. So let's work it out. So we want to rearrange this for m now. So we have m is equal to 4 pi squared over gt squared times r cubed, and r is equal to 50 times 10 to the 3 plus 1.74 times 10 to the 6 meters, which is equal to, what is that? was it 1.74? It's 1.79. Oh, sorry, 1.79 times 10 to the 6 meters. So now we're ready to solve this. We get m is equal to 4 pi squared over 6.67 times 10 to the negative 11 times the period, which was 6.78 times 10 to the 3, all squared. And then we want to multiply that by r cubed, which is 1.79 times 10 to the 6 cubed, which gives us, what was it? We had 4 pi squared, 4 times pi squared divided by 6.67 times 10 to the 11 negative times 6.78 E3 squared. And we'll close that bracket, and that's equal to, then we want to multiply that by r cubed. .79 times 10 to the 6 cubed equals a very big number. So we got, this unfortunately doesn't do scientific notation, but we go 3, 6, 9, 12, 15, 18, 21, 22. So it's 7.38 times 10 to the 22 kilograms.